Hi everyone, this is Alice Gao. In this video, I will talk about overfitting. This is a common problem when we're learning a decision tree. As a model for supervised machine learning, a decision tree has several nice properties. Decision trees are simpler. They're easy to understand and easy to interpret. When it's important to explain a model to another human being, a decision tree is a good choice. In contrast, a neural network is often complex and difficult or impossible to interpret. Also, decision trees can produce a reasonable model even if you have a tiny data set. In contrast, a neural network often does not work at all with a small data set, and it is extremely prone to overfitting. Even though decision trees have so many nice properties, overfitting is still a common problem when we're constructing a decision tree. Let me give you an example of a scenario where a decision tree can overfit to the data. After that, let's look at some strategies to prevent overfitting. Our Jeeves dataset has 14 data points. This is an extremely small dataset, but we can still learn a reasonable decision tree for this dataset. If you read through the full example that I showed you, you will generate this decision tree shown on the current slide. I used the expected information gain metric to choose the feature to test at every step. The test error of this decision tree is 0 out of 14. In other words, it predicts all of the test data points perfectly, which is great. Suppose that you send the training set and the test set to your friend. For some reason, the dataset gets corrupted during the transmission. Your friend gets a corrupted training set where only one data point is different. For this third data point, it changed from the label yes to the label no. This is a tiny change to the training set. But how would this change affect the decision tree that we generate? This is a good practice problem for you. If you want some extra practice, pause the video now and generate a decision tree based on this corrupted data set. Here's a decision tree that I generated using the corrupted training set. Only the middle branch of the tree is different. Instead of making a decision right away when Outlook is overcast, we need to go through a small subtree. We need to test humidity first and then possibly test wind afterwards. The test error of this new tree is 2 out of 14. This tree misclassifies 2 data points in the test set. What happened here? We grew an entire middle subtree to accommodate one corrupted data point. So this small corruption caused a dramatic change to the tree. We also ended up having a larger test error, making 2 mistakes instead of 0 mistakes before. This new tree is more complicated, and it likely won't generate well to unseen data. So why did this happen? The main reason is that the decision tree learner algorithm is a perfectionist. The algorithm will keep growing the tree until it perfectly classifies all the examples in the training set. However, this is not necessarily a desirable behavior, and this can easily lead to overfitting. Instead, it would be better to grow a smaller and shallower tree. The smaller and shallower tree may not predict all of the training data points perfectly, but it may generalize to test data better. Let me talk about some strategies we can use to prevent overfitting when learning a decision tree. You will explore some of these strategies in the assignment. At a high level, we have 2 options. we can stop growing the tree early. This is called pre-pruning. Or we can grow a full tree first and then trim it afterwards. This is called post-pruning. Let me talk about pre-pruning first, which means we'll stop growing the tree early. When should we stop growing the tree? There are several criteria we can use, and I'm going to talk through all of them. If we decide not to split the examples at a node and stop growing the tree there, then we may still have examples with different labels. If it's a binary classification, then we will have examples with both positive and negative labels. At this point, we can decide to use the majority label as the decision for that leaf node. Here are some criteria that we can use. Maximum depth. We can decide not to split the examples if the depth of that node has reached a maximum value that we decided beforehand. Minimum number of examples at the leaf node. We can decide not to split the examples if the number of examples remaining at that node is less than a predefined threshold value. The third criteria, minimal information gain. We can decide not to split the examples if the benefit of splitting at that node is not large enough. We can measure the benefit by calculating the expected information gain. In other words, do not split examples if the expected information gain is less than the threshold. The last possible criteria, reduction in training error. We can decide not to split the examples at a node if the reduction in training error is less than a predefined threshold value. For pre-pruning, we will split the examples at a node only when it's useful. We can use pre-pruning with any of the criteria above. A better method is post-pruning. Grow a full tree first and then trim the tree based on some criteria. Post-pruning is particularly useful when any individual feature is not informative, but multiple features working together is very informative. Let me give you an example. Consider a dataset with two input features. Both features are binary. The target feature is computing the XOR function of the two input features. That means the target feature is true if and only if the two input features have different values. For this dataset, each input feature alone tells us nothing about the value of the target feature. However, if I know both input features, then I know the target feature for certain. For this example, what's going to happen if we produce a decision tree using pre-pruning versus post-pruning? With pre-pruning, we will test none of the two input features. Testing each feature gives us zero information. So we'll end up with a tree that has only the root node, and the tree will predict the target feature randomly. With post-pruning, we will end up growing the full tree first, which means testing both input features in some order. Afterwards, we will try to see if we can prune any of the node. And it turns out it's not a good idea to prune any node because the second input feature in the order is going to give us all the information that we need. So we'll end up growing a full tree, and the full tree will predict the target feature perfectly. I hope this example showed you that post-pruning can be better than pre-pruning. Post-pruning helps us recognize the cases when multiple features working together will be very beneficial, but any of the features individually will not be very useful. We can apply post-pruning to any of the criteria I've described above. we only need to be careful in one aspect. We will only decide to prune a node if it has only leaf nodes as its descendants. In other words, if we have a node where some of its descendants are leaf nodes, whereas some of its descendants are subtrees and not leaf nodes, then we'll not consider that node for post-pruning. For example, suppose we're considering post-pruning with the minimal information gain metric. First of all, we'll restrict our attention to nodes that only have leaf nodes as its descendants. Add a node like this if the expected information gain is less than a predefined threshold value. Then we will delete this node's children, which are all leaf nodes, and then we'll convert this node to a leaf node. There has to be examples with different labels at this node, possibly both positive and negative examples. We can make a majority decision at this node. That's everything for this video. Let me summarize. After watching this video, you should be able to do the following. Explain how and why overfitting occurs when learning a decision tree. Describe strategies to prevent overfitting when learning a decision tree. Compare and contrast pre-pruning and post-pruning. Explain why post-pruning is better than pre-pruning. Thank you very much for watching. I will see you in the next video. Bye for now.